This is lecture 5 on scattering in 3 dimensions. It's part of a mathematical physics course, theoretical physics, on topic of quantum mechanics. It's at senior level, and the first author of the text I'm using is Davies, and here's the text. 2 authors, Paul Davies and David Betts. It's a 2nd edition. You can find this book for free on emule, E-M-U-L-E, emule.com, or if you prefer it in hardback, paper version, hard copy, you can go to this website at Prof. Hugo deGaris, Prof short for Professor. Hugo deGaris is my name, family name deGaris, a French sounding name, although I'm not French. WordPress.com, and there you'll get details of the course and prices of this book on Amazon.com and so forth, and chapter headings and right. So chapter 5, lecture 5, one chapter per lecture, although the lecture's split up into many parts, many clips. Now, so this topic is basically on scattering, and probably one of the most important concepts for the first few sessions is the notion of cross-section. A section is the resulting, what you get from a cut. If you take a watermelon, for example, and you take out a machete or a Japanese samurai sword and you slice the melon, the flat part that results from one part of the melon, that flat part is called the cross section. Section, yeah, like cut, the result of what gets cut. And that idea is relevant to scattering, but it won't become clear for a while, a couple of sessions, why it's called that, but you will see in time. Now, the importance of scattering is high, because the kind of thing, well, in particle physics, for example, most of the knowledge that's been obtained in particle physics has come from scattering experiments. For example, the most famous atom smasher in the world today is the LHC, the Large Hadron Collider, in Geneva, Switzerland, on the Swiss-French border. Recently it was confirmed the existence of the long sought after Higgs boson that gives mass to particles. So what those guys at LHC are doing is effectively they're just scattering. They're smashing particles into each other. Now, in this case, we'll start off with a simpler case. We'll just send particles, like a beam of particles, approximated very simply by a uniform wave front, just sort of moved like as a surface, like here's the surface, and just moving in, let's say along the x-axis, to a target, let's say here on the x-axis. Let's say that's x is 0 here, this target, and it's heavy. It doesn't move. It doesn't get jolted or by this incoming wave or wave front. Right? That's an approximation, but we'll keep things simple to start with. To do in fact, solving the Schrodinger equation yet again. So this is the last chapter of 4 on solving the Schrodinger time-independent equation. So this session is basically introductory, and so is the next one, introducing you to the concept of cross-section, which is a critical concept when discussing scattering. And I'm trying to emphasize the importance of scattering to quantum mechanics, because it's the basic tool. Scattering is a basic tool to learn about the properties of the elementary particles, and it's the elementary particles that constitute nature, right? Well, maybe you've heard lately that about 3/4 of the known energy in the universe is actually dark energy, and we have no clue what it is. Well, some clues. We know it's responsible. It's hypothesized to be the source, the cause of matter accelerating away, galaxies accelerating away from each other, because one of the big discoveries, I think 1998, was that the universe is actually accelerating away from the center. So, major discovery, and the source of that, the cause of that is thought to be dark energy. And another quarter, a bit less, is so-called dark matter, distinct from dark energy. And dark matter is needed to explain why our galaxies don't fly apart. There's about 10 times more dark matter than there is ordinary matter. And that dark matter is needed to hold and pull gravitationally, pull the universe together, otherwise it would fly apart at the speed that it's going. And so the elementary particles that we know about is a mere, I think, about 4% of the energy in the universe. So it's, in some ways it's rather humbling, but there you are. But of what we know, most of the knowledge obtained about elementary particles, basic particles, is obtained from scattering experiments. So scattering, a very, very important concept, right, for quantum mechanics, right? So that's sort of what I've been saying. So the model we're going to start with is you have, you can see here, scattering center. So you have this target just here in the middle, and you send in a beam of particles. Just imagine a wave front coming in. This is the x direction, this way. So this beam's coming in this way, and it gets scattered. These particles. Depending, like, if you have a particle that's coming dead on to the target here, it'll certainly be scattered, and there's a certain potential generated by this target or scattering center, and so depending on the distance r from the target and the incoming particle, the degree of scattering or deflection, if you like, will depend on that r, and that creates a certain symmetry in the following sense. The